Record. Okay, so your test on Thursday will cover parts of 2.3. We're not going to finish 2.3, but you'll be happy that we're going to cover at least part of it. I will put a turn-in tray for 2.1 worksheet and notes for you this afternoon. I'll put that in there, and then I'll remind you in class tomorrow to turn it in. Yeah. We're going to come back to 2.2. We'll circle back to 2.2. 2.2 is just derivatives on the calculator. I kind of just showed you that at the end of class last time. But there's a whole nother mess of that. But I want to make sure we get this covered today so you can be excited about it. 2.3. 2.1 worksheet, when should we make that due? Let's just make that due Thursday for the test, okay? Yeah, Thursday. Yeah. And then 2.3 worksheet, we're probably not going to finish it, so it won't be due before the test. But in 2.3, we're going to basically learn what I call the shortcut rules, but they're not just like gimmicks. They're actual rules that are established out of the theory and the calculations that we've already looked at, namely the limit definition of the derivative. But there are patterns that emerge that you can then kind of take the back door to getting onto the stage like Willie Nelson does at Green Hall, rather than have to fight the crowd and come through the front door. So the first thing I want to point out are these two accent points. I don't want to call them bullet points anymore in school, but they're accent points. dy dx, that's Leibniz notation for the derivative. It's a noun. We call that the derivative of y with respect to x. Again, it kind of looks like delta y delta x, which is your finite slope from algebra 1, average rate of change. This is the infinitesimally small at a single point derivative of y with respect to x. It's a noun. d dx, okay? You could think of the y as being movable. You can actually take the y out of the numerator and put it out front. When you write it like that, it becomes d dx of y, and that's a verb. That is kind of like an instruction. Hey, take the derivative with respect to x of what follows. All right? So dy dx is a noun, and d dx is a verb. So if you were to like say d dx of y, that would actually equal dy dx. Okay? How do we take the derivative with respect to x of y? Well, it becomes the derivative of y with respect to x. So dy dx is a noun. It's the exact same thing as y prime. It's the exact same thing as f prime, okay? But d dx is a verb. The instructions are contained within. All right, so the first rule that we're going to learn here, real easy rule. It's a constant rule. And it's called the constant rule because it never changes. It's been the same rule every year I've taught it, right? That happens to be true, but that's not why it's called a constant rule. It's called a constant rule because it tells you how to take the derivative of a constant. And here it is. It's that simple. The derivative of a constant is always zero. Always zero, okay? And you can look at it any number of ways. If I say, give us any constant y equals c, where c is any number, if you want to look at it graphically, what does the graph of a constant look like? What type of straight line? Horizontal straight line. Yeah. And if the derivative graphically gives us the slope at any point, the slope of a horizontal line at any point is zero, anywhere and everywhere. If you want to think about it in terms of Newtonian perspective, the derivative gives us the rate of change, okay, at any point. Well, by definition, how much does a constant change? It doesn't, right? It doesn't. So if you had to quantify no change, it would be zero, right? Constants by definition don't change, so their quantifiable numerical rate of change value is zero. All right, let's try it out. Example 1, find the derivative of each of the following functions. If y equals 8, what's the derivative of 8? 0. Now, we got to be careful. We can't just put 0 there. That's meaningless, right? That's just y equals 8, and underneath there you have a 0. That's meaningless. So What we're practicing here is not so much the constant rule, but rather our notation, okay? What we're really doing when we find the derivative of a function, and you don't have to write this step that I'm about to write, but it's kind of what goes on behind the scenes. We're actually taking the derivative with respect to x of both sides. Do your math homework. It's due Thursday. Okay? We're taking the derivative with respect to x of both sides. It's an equation. So whatever we do on one side, we got to do on the other. Now, you don't have to write that. Okay? There is a time when we do this, and it's when we get to what's called implicit differentiation. Right now, since this is an explicit equation, it's solved for y in terms of x, even though there's no x. The method's going to be implied. Now, when we take the derivative of both sides, it is an operation, so it has to go in front on both sides. You can't just like come up here and put d dx in front there, and then over here put d dx. You know, it's not commutative, if you will, right? That doesn't, 8 d dx doesn't make any sense. It's the derivative of with respect to x of what follows. Now, what becomes of the left side? The derivative with respect to x of y is the noun, the derivative of y with respect to x. And on the right side, we'll actually compute it. What is the derivative of 8? What's the instantaneous rate of change of 8? 0, yeah. So there you go. In the future, you can go straight from here to here. You don't just put a 0. Or, if you prefer, you could call it y prime equals 0. Either one. Y prime is again, just shorthand for the derivative. Leibniz notation has the dy dx, and then function notation is the prime notation. All right? Very good, very good. Now let's try it out on part B. If f of x is 0, let's take the derivative of both sides. Bless you. But we're not going to show it like we did on this one here. We'll just use the notation. So on the left side, what is the derivative of f of x? F, well, you could do that, but it's function, so we're just going to put f prime of x. Now, you could say the derivative of f with respect to x. That's just not very common. If it starts with the function notation, we typically keep it in prime notation. If it starts in terms of y, we typically use Leibniz notation. Although y prime is not uncommon. Same thing over here in function, it's not, you know. Right? And then, of course, what's the derivative of 0? 0, right? On this one here, we have s of t is equal to 3. If I take the derivative of the left, I get s prime of t. All right, and what's the derivative of the right? What's the derivative of 3? 0. Good. So again, we're practicing our notation. Another acceptable version over here would be the derivative of s with respect to t. Okay. Bless you. Bless you. And then look at this, part D. If y is equal to k pi squared, where pi is the typical pi and k is some constant, then what would the derivative of y with respect to x be? 0. Yeah, it's still 0, right? Because a constant times a constant is a constant. And there you go. So again, y prime would work here, but typically, again, just conventionally, if we start with y, the derivative, we use dy dx. If we start with function notation, we use the prime notation. F of x becomes f prime of x. All right, so the constant rule, pretty easy, right? You would like to have maybe the whole front part of the test on Thursday will be just constant rule, right? Maybe. You know what? We could actually verify this using the limit definition. Would you want to, or is that's too? No, that's splitting hairs. That's sawing sawdust. Beating a dead horse. It's the same. Who does that? Like, where did that phrase come around? Like, hey, quit beating that horse. It's already dead. No, I just wanted to make sure. All right. This next one is going to be the glorious rule. You're going to love this rule. Okay. No one has never, ever not loved this, except one guy. And I'll tell you the story about him later. He was a professor at UT. It's called the power rule. but I added the word fool at the end, right? The powerful rule, because it is. It's very powerful. Very, very powerful. But it's called the power rule. Here's what it says. If n is a real number and a is also a real number, some constant, in the function f of x equals a times x to the n, we have a coefficient times the power of x. See that? A times x to the n. Some number times x to some power. Then the derivative of that expression, ax to the n, is an times x to the n minus 1th power. I actually gave you a preview of this the other day. If you can write a term in the form number times x to some power, this is x on the ground floor, it's in the numerator, a times some power of x, yes. It works when a is 1, it works when n is 1, it works when a and n are any real numbers, believe it or not. Okay, they don't even have, n doesn't even have to be an integer. Doesn't have to be. But yeah. How do you find the derivative? Well, you either set up the limit as h goes to 0 of f of x plus h minus f of x all over h, and then do one of those algebraic methods like ratcon and lick 'em over lick 'em, or simply get your new coefficient by multiplying those two. Coefficient times exponent gives you your new coefficient. And then, as I mentioned in class, think of it as like, well, I used the exponent, so now it's depleted by 1. Multiply, then subtract. It's that easy. Multiply, and then subtract. It's hard to mess up, right? Is it subtract, then multiply? No. Your dear Aunt Sally, right? Multiply, and then subtract. Holy moly smokers. Let's try it out. Find the derivative of each of the following functions. If f of x is equal to 2x cubed, what's the derivative of the left side? The other left side. F prime of x. Thank you. No, the left side is f. What's the derivative of f? F prime. Notation. Okay, now, on the right side, is it written in the form ax to the nth power? Yes, so we could say it's going to be the limit as h goes to 0 of 2 times x plus h cubed minus 2x cubed all over h. And then we have to hit that with the sledgehammer, right? Cubing a binomial, there's no square multiply double square, and it's not just x cubed plus h cubed. We'd have to go off to the side and figure out what it is, right? Yucky, gross. Or hey, watch this. What's 3 times 2? 6 times x to the, what's 3 minus 1? 2. What? Really? Is it magic? No, it's not magic. It's a result of the limit definition that's done on a general form, ax to the n, using high-powered algebra math. It always comes out to be an x to the n minus 1. I don't know who the first person to discover that, but we've all benefited from it ever since. That is the derivative of 2x cubed. It's 6x squared. So now you can remember where you were the very first time you learned the power rule, because it's going to be part of your life from here on out. It was 1:23 on a Tuesday afternoon. It was World Rabies Day. Yeah. It was on the day that William the Conqueror landed at Pevensey Bay on his way to Hastings, ultimately, less than a month later, a couple of weeks later, where he fought against his cousin's son and became the Norman Emperor or King of England, right? So anyway, yeah, that's where you were. And you did it under the watchful eye of one of the 3 lead guitarists of Iron Maiden, Dave Murray, and their drummer, Nico McBrain. He was watching the whole time. You learned the power rule today. Power rule. That's awesome. It's awesome. So remember what I said, that you're going to have to be able to deconstruct the derivative? If you ever saw this and you said this is the derivative of some function, it would be the derivative of 2, I don't like you, x plus h cubed. And now instead of hitting the sledgehammer, you're like, oh, if that's the derivative of 2x cubed, let me just use the power rule. It's 6x squared. Done. Big time saver. All right, let's try this one. Letter B. G of x is the cube root of x over 3. Oh, wait. The power rule only works if I write it. Yeah. No, great question. I just wrote that because I didn't know the power rule existed. Yeah. So I was, and then someone said, hey, have you ever thought about, no, you don't have to do that. Heck, no, I just kept that there just for compare and contrast purposes, right? Like, no, thank you. Yes, please, right? But you don't have to write it. Now, on the next one, the power rule is powerful, but it only works when I write my expression in the form ax to the n. That's not quite what I got here, right? So sometimes there's a little work on the front end, right? So I'm going to write that as 1/3 times x to the 1/3 power. Is that in the form ax to the n? Ax to the n. Bingo! G prime of x then. Don't forget the left side. Multiply, then subtract. Multiply, and then subtract. What's 1/3 times 1/3? 1/9 times x to the 1/3 minus 1. Well, 1 is the same as 3/3, right? So 1/3 minus 3/3 is negative 2/3. When you clean this up, and it's always good idea to clean it up, put it back into the original format. No negative exponents, no radicals. That's the same as 1/9 times the cube root of x squared. Holy moly smokers. If you think about what the parent function is to g of x equals the cube root of x over 3, it's the cube root of x, which we know is continuous at the origin, isn't it? But is it differentiable at the origin if it goes vertical right there? No. Do you think the derivative knows that it's not supposed to exist at x equals 0? I mean, really, how could it even know that? It does! Look, g prime of 0 is 1/0. That's some type of infinity. It knows the slope is infinite there. The x jumped from the top to the bottom. It knows. They're communicating through the mathematical ether somehow. Hugely cool. Yeah, sweet. Sweet. Radical. Hey, that's totally radical. Tubular. Hey, let's try this one. 5/3x to the pi's power. Ooh. Can I just say that this is y prime equals 5 over and then go 3 pi times x to the pi minus 1? Well, that's actually a negative. No, why not? Because this is not written in the form ax to the n. My x is in the denominator. That's not good. I need to be able to write it in the form a times x to the nth power. That's all over 1, really, right? So this, if I rewrite it as y, could become 5/3 as my coefficient, and then x to the negative pi. Now is that of the form ax to the n? Yes. So the left side becomes dy dx, or y prime. And now we multiply, subtract, multiply, subtract. So when I multiply, I get negative 5 pi thirds times x to the negative pi minus 1. Pi is an irrational number. It's a transcendental irrational number. But it works. Multiply and subtract. And now if I clean that up, negative 5 pi stays in the top, 3 goes to the bottom, and now the x goes to the bottom. And what's my new exponent in the bottom? Is it pi minus 1 or pi plus 1? Pi plus 1. I got to change the sign of the exponent, which because it's two terms, I would have to distribute the negative. Okay? So it becomes pi plus 1. Yeah, that is so hot. I mean, is that what you meant? Oh, okay. Right. Like, ooh, purple pie. Right? Now, I want to just show you kind of what a huge time saver this is. Let's look at part B. If I were saying g prime of x is the limit as h goes to 0 of the cube root of x plus h minus the cube root of x all over h, and then that was over 3 and over 3, yikes. I would first have to do lick 'em over lick 'em to get rid of the 3, and then I'd have to do some crazy ratcon with cubics. How would you do ratcon with a cube root instead of a square root? You'll no say. I don't know. Like from here, it's just like a big question mark, huh? Guess it can't be done. And over here, it would be y prime equals the limit as h goes to 0 of 5 over 3 times x plus h to the pith power minus 5 over 3x to the pith all over h. And now you'd have to do some kind of ratcon, but eventually you're going to have to hit it with the sledgehammer. You tell me, how do you expand x plus h to the pith power? How do you do that? Pascal's triangle doesn't even work there. It's not x to the pith plus h to the pith. I know what you pre-calc kids are thinking. Like, how do you do that? It's just like, I guess it can't be done. No, it can. And the power rule tells us how. Not only does it tell us how, but it gives it to us relatively quickly with few steps, and that means the likelihood of making a careless mistake is much smaller than if we even knew how to algebraically compute these two limits. Yowza. Okay? But it does have to be written in the form ax to the n, right? That's the only trade-off, right? Let's look at letter D. Y equals 6 over the 5th root of x cubed. Is that written in the form ax to the nth power? No. Can we get it like that, though? Yeah, so don't call it y prime yet. It's not y prime yet. It's still just y. That's going to be 6 times x to the what power? Can you do it in one? Negative 3/5. Good. If you can do it in one step, that's great. Now it's in the form ax to the nth. So here we go. Y prime or dy dx, that's the derivative of the left, and multiply, subtract, multiply, subtract. 6 times negative 3/5 is negative 18/5, right? Because that's 6 over 1. You multiply straight across. Times x to the subtract. Negative 3/5 minus 1 is the same as negative 3/5, bless you, minus 5/5, which is negative 8/5. There you go. Multiply and subtract. We're doing stuff right now that Galileo never was able to do. He spent his whole life trying to do this. Galileo couldn't even multiply and then subtract. Galileo, if you just would have learned your arithmetic, right? You think Galileo knew how to multiply and subtract? Yeah, he did actually. He knew how to multiply and subtract with the best of them. But you know what he didn't know? He didn't know that in a problem like this, if you simply multiplied and subtract, you'd get the function that gave you the instantaneous rate of change. That's what he didn't realize. Because without knowing why this works, which is a distillation of the limit definition, which he didn't know either, it seems arbitrary, right? Oh, you multiply and subtract? Oh, okay. Because I thought it was like divide and then, ding dong ditch your neighbor. I thought that was the sequence, right? Divide and then do some ding dong ditching, I thought that gave us the derivative. That seems pretty arbitrary. Multiply and subtract. I wanted to get another activity in besides something mathematical. I don't know why I was thinking of ding dong ditching, but maybe it had something to do with the fact that people were knocking on the door and I wasn't allowed to open it. I don't know. Number, how is it? Is that awesome? That's freaking awesome. Look, does it work up here for constants? Let's try it. Let's try it. I can rewrite 3 as 3 times t to the 0th power, right? All right, so the left side's derivative is s prime of t. Let's try the power rule. Multiply, 0 times 3 is 0, times t to the subtract, 0 minus 1, negative 1. Oh, that's the same as 0 divided by t. Well, what's 0 divided by t for any t that's not 0? 0. It works. The power rule. Ax to the n has to be in that form. The derivative is an x to the n minus 1. You're welcome. You're welcome. But it's not a gift from me. It's a gift from these two guys. Look how happy they are that you have it. Dave Murray is a jolly guy. They're all actually pretty jolly. But you know, when you pose for the band picture, you have to like look tough. And it's hard for Dave Murray to look tough because he's such a nice guy. All right, we're done with that section.